Engineering thermodynamics. We are discussing about some of the basic concepts of engineering thermodynamics. In this session, we are going to discuss about the work transfer during various quasi-static processes. The outline of the presentation is like this. Let us start with the derivation for various quasi-static processes with reference to the work transfer. And the sum of the process are isobaric process, which is nothing but the constant pressure process. Followed by that, we are going to discuss about isochoric process, where volume is held constant, and in the case of isothermal process, temperature is going to be maintained constant. And for isentropic process is nothing but a reversible adiabatic process. And finally, we are going to discuss about the polytropic process, where the index of expansion is given as n. The value of n can vary from 0 to infinity. And finally, we are going to discuss about the free expansion process. Let us have the recap of the previous lecture. In the previous lecture, we have discussed about displacement work or PDV work. In the case of displacement work or PDV work, there are 4 points to be remembered. This expression, work transfer equal to integral PDV, this is applicable for a closed system. Point number 1, it is applicable for a closed system. And if you want to calculate the infinitesimal work for a closed system while undergoing a process, if you want to determine the infinitesimal work, then it is given as delta W equal to PDV. Remember, there we have written dW. It should not be written as dW. Instead, we are going to write it as delta W. I will tell you the reason. One, we are going to discuss about the path function and point function. And if you are going to determine the total work done during this expansion process for a closed system, and assume that it is going to be a quasi-static process, then it is given as work transfer W1 to 2 during the process 1 to 2 is given as integral PDV between the states 1 to 2. And at state 1, volume is V1, at state 2, volume is V2. So the limits are going to be V1 to V2. And the third point is the area under the curve in a PV diagram represents work transfer. Right? That we have to remember. And the fourth point to be remembered is that this expression integral PDV is applicable only for a quasi-static process. Right? Quasi-static process, we know that it is a reversible process, and during this process we are going to have infinite number of intermediate equilibrium states, and the process is going to occur at very slowly. Let us go for the expression for work transfer during various quasi-static processes. Let us start with constant pressure process. Constant pressure process is also called as isobaric process. And if you represent this process, this expansion process in a PV diagram, if you express this process in a PV diagram, then it is going to appear as a horizontal line. Right? This is constant pressure expansion process. Right? For a closed system undergoing a quasi-static process. Okay, so state 1 is the initial state, state 2 is the final state. When it undergoes expansion, volume is going to increase because pressure is held constant. And the area under this curve is going to represent the work transfer. So to determine the work transfer, it is integral PDV between the states 1 to 2. Now the governing equation is P equal to constant. Right? If the pressure is constant, for isobaric process, pressure is constant, so we can take this P outside. So it will become integral dV. When we integrate dV, it will become V, and we are going to apply the limits V1 to V2. So P into V between the limits V1 to V2. When you apply the limits, it will become V2 minus V1. So work transfer during a constant pressure process is P into V2 minus V1. So this we have to remember. So for any quasi-static process undergoing constant pressure, during that process, if the pressure is constant, then the work transfer is given as P into V2 minus V1. Coming to the next process, that is constant volume process, which is also called as isochoric process or isochoric process. So in this process, we are going to have a vertical line. The expansion process is represented by a vertical line. This is the initial state where pressure is P1 and volume is V1. And when this constant pressure expansion takes place, pressure is going to get reduced. Pressure will get reduced to P2, and the system will reach state 2. And the pressure and the volume V2 and V1 are same. Right? At state 1 volume and state 2 volume both are same, where the pressure is going to vary. So this is during a constant volume process. And since this process is a quasi-static process, we can apply integral PDV. So work transfer is integral PDV between the limits 1 to 2. this volume is constant now. For this process, volume is constant. So if it is constant, then dV is going to be 0. So 0, if you integrate, then we will get 0. Right? So the work done during a constant volume process is 0. So this we have to remember and make this point, make note of this point. Work transfer during a constant volume process is 0. And the next process is isothermal process or constant temperature process. The expansion in the case of an isothermal process, it will be like this. This is the initial state and this is the final state. When it expands, we are going to have fall in pressure and increase in volume. At state 1, volume is V1. At state 2, volume is V2. So there is an increase in volume. Where the pressure at state 1 is P1 and the pressure at state 2 is P2. And P2 is less than P1. Now let us calculate the work transfer during this isothermal process. Work transfer during isothermal process is given as integral PdV between the states 1 to 2. And the governing equation for isothermal process is PV equal to constant. PV equal to constant. So from this, what is the value of P? C by V. P equal to C by V. So this C by V I am going to write in place of P. So then work transfer will become integral 1 to 2 C by V into dV, where C is constant. Since C is constant, that can be taken out of the integral symbol. So it will become W1 to 2 equal to C into integral 1 to 2 dV by V. If you integrate dV by V, then we will get ln of V, right? Natural logarithm of V. So for that, if you substitute the upper limit and lower limit, then it will become ln of V2 minus ln of V1, right? So this can be simplified as work transfer equal to C into ln of V2 by V1, where C is nothing but PV, because this process is PV equal to constant. So substituting this, then we will get work transfer during an isothermal process equal to PV into ln of V2 by V1. Or I can say, instead of PV, I can write P1 V1, or I can write P2 V2. Okay, so this expression refers to the work done during a constant temperature process or isothermal process. Now coming to the adiabatic process, right? And we are discussing all these processes are quasi-static process. Quasi-static means reversible process. Reversible adiabatic process is what we call it as an isentropic process. Till now we didn't discuss anything related to entropy. Entropy is a property, right? You make sure that entropy is a property, and in detail we will be discussing about this property entropy when we are discussing about second law of thermodynamics. So as of now, you consider that entropy is a property, thermodynamic property. Right, for this the governing equation is PV power gamma equal to constant. The governing equation for an isentropic process is PV power gamma equal to constant, where gamma is Cp by Cv of the gas, right? Specific heat capacity at constant pressure and specific heat capacity at constant volume. That ratio is what we call it as gamma. So PV power gamma equal to constant. Now let us represent this process in a PV diagram. So along the y axis we are having the property pressure. Along x axis we are having the property volume. So the expansion during an adiabatic process or reversible adiabatic process or an isentropic process is like this. It starts from state 1 to state 2, and the governing equation is PV power gamma equal to constant. Now I want to determine the work done during this expansion process, isentropic expansion process. We want to determine the work done. So work done for a quasi-static process given as integral PdV between the states 1 to 2. And the governing equation is PV power gamma equal to constant. From this, the value of P. The value of P from this is C V power minus gamma. So this C V power minus gamma I am going to substitute in the place of P. So work transfer equal to integral 1 to 2 C V power minus gamma into dV. So if you integrate this, C can be taken out outside because this is constant. So this will become V power minus gamma plus 1 divided by minus gamma plus 1. So C into V power minus gamma plus 1 divided by minus gamma plus 1 between the limits of states 1 to 2. At state 1 volume is V1, at state 2 volume is V2. So in place of V, we are going to substitute the upper limit and lower limit. So it will become V2 power minus gamma plus 1 minus V1 power minus gamma plus 1 divided by minus gamma plus 1. So that is what is given here. But remember, the value of C is PV power gamma. Value of C is PV power gamma. Or we can say P1 V1 power gamma or P2 V2 power gamma. So this I am going to multiply, or I am going to take it inside this bracket. So when I take it inside here, I am having V2 power minus gamma plus 1. So therefore I will be writing this. When I take this C inside, I can write this as P2 V2 power gamma into V2 power minus gamma plus 1. Whereas when I take it here, I am having V1. So in terms of V1, I am going to express C. So which is nothing but P1 V1 power gamma into V1 power minus gamma plus 1. right? So when we take this value inside and multiply with V2, then finally we will end up with, when you take this as V2 power gamma, here V2 power minus gamma plus 1, that will become V2. So we will get work transfer during the isentropic process is P2 V2 minus P1 V1 divided by minus gamma plus 1, or we can write P1 V1 minus P2 V2 divided by 1 minus gamma. So this is an important relation to determine the work transfer during an isentropic process. Let us come to polytropic process. Polytropic process is similar to isentropic process. Wherever we are having gamma, we are going to replace it by n. So the index of expansion during the expansion process is given by n. And the value of n can vary from 0 to infinity. If the value of n is 0, PV power n, right, equal to constant. That is polytropic process governing equation. If we are going to replace n by 0, then it will become P equal to constant. So it represents a constant pressure process. If the value of n equal to infinity, then V is dominating compared to P. So I can say this is a constant volume process. So that is given here. So in between 0 to infinity, whatever value you are going to have, let us say if the value of n equal to 1. Then if the value of n equal to 1, then it becomes PV equal to constant, which is nothing but an isothermal process. That is given here. As the value of n keeps on increases, then the slope of the expansion curve is also going to increase. As the value of n keeps on increases, the slope of the curve is also going to increase. So we are going to start with the initial state 1, and the expansion process, the end states are going to be different. Right? As the value of n increases, then the slope of the curve is also going to increase. So in general, for a polytropic process, the governing equation is PV power n equal to constant. For this process, I am going to determine the work transfer. Work transfer W1 to 2 equal to integral PdV between the limits of the states, state 1 to state 2. So from this, what is the value of P? P equal to C V power minus n. This is exactly similar to your isentropic process derivation. Wherever we are having gamma, we are going to replace it by n. So instead of P, I am going to write C V power minus n into dV. If you integrate this, the C is constant, you can take it outside the integral symbol. So this is C, V power minus n, if you are going to integrate, we will get V power minus n plus 1 divided by minus n plus 1 between the limits V1 to V2. At state 1, volume is V1, at state 2, volume is V2. So we are going to substitute the values of V2 and V1 in place of V. So if you substitute, this is C into V2 power minus n plus 1 minus V1 to the power of minus n plus 1 divided by minus n plus 1. Correct. So now let us replace this by PV power n. C, I am going to replace it by PV power n. When this is going to be taken inside, for this I will write as P2 V2 power n. Whereas here, when I bring this PV power n here, I will write it as P1 V1 power n. And after simplification, finally we will get P2 V2 minus P1 V1 divided by minus n plus 1. Right? Or we can write this work transfer equal to P1 V1 minus P2 V2 divided by 1 minus n. Right? Both are same. So this is an expression for a polytropic process, for a system undergoing a polytropic expansion process, and this is the work output from the expansion process. Now let us consolidate all the process. Before we consolidate, let us go to the free expansion process also. So remember, work transfer is a boundary phenomenon. Work transfer is nothing but energy in transit, and that energy transit is felt only at the boundary. So work transfer is energy in transit, and this energy transit is felt at the boundary. Therefore, it is called as a boundary phenomenon. Right? The expansion of gas against vacuum is what we call as a free expansion. Means without any resistance, if a gas expands, that we call it as free expansion process. For this, let us consider like this. There is a chamber, and that chamber is divided into two with the help of a partition. Right? One side of the chamber we are having pressurized gas, whereas the other side of this container, this region, we are going to have vacuum. So one region is pressurized gas, other region is vacuum. Both are separated by a partition. Now let us say I am going to remove this partition. Now what will happen? The pressurized gas that is present in this region, that will expand throughout this container. Right? That will expand throughout this container, and the entire container is going to be occupied by the gas. But remember, the pressure of the gas is going to come down. And remember, both this container are completely insulated. Now I am going to represent this process, this expansion process, in a PV diagram. In a PV diagram, let us say I am going to represent the state 1. At state 1, pressure P1 is higher. Right? This complete I am going to consider as a system. right? So pressure P1 is higher, and at this point the for this region where the pressurized gas is present, pressure is higher whereas volume is less. When we remove the partition, then the gas expands and it will occupy the entire volume. So volume has increased but pressure has decreased. This is represented by state 2. So now we don't know the path followed by the system. Now the gas has expanded, but we don't know the path followed by the system. Now let us say I want to determine the path followed by the system, right? Similar to a quasi-static process, I want to make this expansion process also to occur very slowly. If that is the case, then this vacuum region I should have many number of partitions like this, right? Consider that I am going to have many partitions and of very small thickness, negligible thickness. Now one by one I am going to remove the partition. When I remove the partition slowly, let us say I am going to remove this very first partition, then the gas is going to occupy up to this volume. Its pressure is going to come down, volume is going to increase. Now let us say I am going to measure the pressure and volume and I am going to note down in the PV diagram. Similarly, when I remove the second partition, then I am noting down the pressure and volume, corresponding pressure and volume. Similarly, I am removing all the partitions one by one. So I can mark the pressure and volume in the PV diagram, right? So finally, I will be able to identify the path followed by the system during this expansion process. And now I am tempted to determine the work done during this process, because area under this curve, area under the PV diagram, area under the curve in a PV diagram represents the work transfer. I am tempted to determine the work transfer. But the story doesn't stop here. Now listen carefully. Even though we have some area to determine and we can claim that this is the work transfer, but for a free expansion process there is no resistance involved. Remember, there is no resistance involved, and similarly this process is not a quasi-static process. The integral PDV that can be applied to determine the work transfer only for a quasi-static process. Similarly, the area under the curve in a PV diagram can be used to determine for a quasi-static process, work transfer during a quasi-static process. But this process is not a quasi-static process. How do we say that this is not a quasi-static process? Quasi-static process is nothing but a reversible process. Whatever the path followed by the system during the expansion has to be followed when the process is going to be reversed. Right. Now let us say after removing the partition completely, right? Now the system has come to state 2. Now assume that I am going to again place the partitions back into this slot, right? Your gases will not move from here to the compressed gas region, right? You will not have vacuum here and you will not have the compressed gas here. That will not occur. That will not happen on its own. So this process is not a reversible process. Once the expansion completes, that's all. Then it will not, whatever gases that has moved to the vacuum region will not come back to the pressurized region on its own. So we cannot claim that this process is a reversible process. When this process is not a reversible process, then this is not a quasi-static process. If this is not a quasi-static process, then we cannot apply this integral PDV, or we cannot say that area under the curve in a PV diagram represents the work transfer. That cannot be applied. That is applicable only for a quasi-static process. Now, since this process is not a quasi-static process, so let us say if you are going to consider this entire volume as a system, right? Both the pressurized gas chamber and the vacuum region, both together, these two regions we are going to consider as a system, then there is no change in volume. When there is no change in volume, for a constant volume process, work transfer equal to 0. Right? But if you are going to consider this portion alone as a system, right? If you are going to consider this as a system, then we are having change in volume. Then we are tempted to determine the work transfer using this integral PDV. But during this process, the gas expands against vacuum. Remember, gas expands against vacuum, and also this process is not a quasi-static process. So we cannot determine the integral PDV to determine the work transfer. Right. So this process is not quasi-static, and there is no resistance for the gas to expand at the boundary, right? Because it is going to expand against vacuum. When there is no resistance, then we say that the work transfer is not there. Then the work done during a free expansion process is 0. Since vacuum does not offer any resistance, then the work transfer during this free expansion process is 0. Right? So now let us consolidate the list of process whatever we have discussed. and we will try to write the expression for the work transfer. Okay, so if it is a isobaric process, constant pressure process, then the work transfer is given as P into V2 minus V1. For constant volume process, that is isochoric process, work transfer is 0, right, because there is no change in volume. For isothermal process, work transfer is given as P1 V1 ln of V2 by V1 or P2 V2 ln of V2 by V1. For an isentropic process, then it is P1 V1 minus P2 V2 divided by gamma minus 1 or P2 V2 minus P1 V1 divided by 1 minus gamma. Right. For a polytropic process, index of expansion is n. So we can replace this gamma by n. So work transfer during a polytropic process is P2 V2 minus P1 V1 divided by 1 minus n. And remember, for all these processes are quasi-static processes. Only if it is a quasi-static process, then we can apply this integral PdV or area under the curve to determine the work transfer. And finally, we have discussed about the free expansion process. For a free expansion process, work transfer is 0 because the expanding gas is not going to face any resistance. That is, vacuum is not going to offer any resistance. Therefore, for a free expansion process, work transfer is 0. This is to show that during which condition work transfer is going to be 0. So from physics, we know that work equal to force into displacement, right? So if the displacement is 0, right, work is nothing but force into displacement. If the displacement is 0, then we say work transfer is 0. This is one condition. And the other condition is that if the resultant force acting on the body becomes 0, work transfer equal to force into displacement. If displacement is 0, then work transfer is 0. If resultant force acting on the body is going to be 0, then also work transfer is 0, right? And another condition is that if the direction of force applied is perpendicular to the displacement of the object, then also work transfer is 0, right? So these are the cases during which we will have work transfer as 0. Thank you for joining the session.